All right, hey everyone. First thing is, I want to let you know that in the meeting chat, I put announcement from Yearbook. I think they want to try to get as many students to take their poll. So if you're in the classroom, you can check that out in the meeting chat, either now or later. So just to let you know. Let's see. I have a couple more announcements here. Let me see. All right, first is today we're going to be continuing working on optimization problems. Realize I'm not going to have a chance to start test review, but it's okay. We can kind of get more comfortable with the different scenarios for optimization today. We're just going to work through this worksheet that we started yesterday. And we're going to be able to start our test review on Friday. Okay, so tomorrow no class, PSAT. So Friday we'll start our test review. I'll have the links ready for you to access and to print if you need to. So that'll be on Friday. Monday we need to start chapter 5. Okay, but chapter 5, just 5.1, not going to be on the test, but just so that we're not able to kind of keep up with our calendar. So, but it shouldn't only take, half the class period. We'll have a second half to do more test review. So we'll do some test review on Monday. Tuesday, no school. And then Wednesday, we'll do another full class period of test review. So we'll have 2.5 days of test review, Friday, Monday, and Wednesday, and then tests next Thursday. Okay, test is next Thursday. Another announcement is I want to start holding consistent daily help sessions in the morning and afternoon. So you can come in the classroom to do a help session, or you can be on Teams. I'll have it open and for either scenario, and I'll record each of the help sessions. So I'm going to start with that this afternoon, 3:30. Probably going to go over some optimization problems and answer any questions you have about derivative graphs. We can do some practice of those as well. And I'll record each session, so if you're not able to make it, you can kind of check and see what's discussed. Tomorrow morning, I can't do it because I have to do PSAT prep, but tomorrow afternoon and then Friday morning. So yeah, I'm going to try to keep it consistent. If there's a change where I can't make it, or if there's a change in the day and the time, I will I'll probably send out a text remind for that. And I've already reached out to some of you who I think could benefit from these reviews. So if you haven't responded, if I reached out to you, if you haven't responded, just take some time to respond back to me and let me know what you think. Okay. I've graded most of your quizzes, your 3.1, 3.4 quiz. there's still a couple that I haven't gotten to, so I'm gonna try to work on that, finishing that up. I hope to hand back your quizzes on Friday or return them to you through Teams, depending on how you took it. And tentatively, probably looking at a recovery date of next Friday, so day after the test. If you score below a 79 or below, you can you're eligible to take that test or to retake that that quiz for a higher grade. Okay, but I'm still working out the details there. All right, any questions that you guys have? Okay, let's go to the review, the practice worksheet. And let me just spend a little bit of time just kind of recapping what we covered at the end of class yesterday. All right, so we talked about how optimization, the first step is deciding what equation we're going to be focusing on. So you look for these keywords, right? Largest, smallest, optimal, greatest, right? Those keywords, and see what it's describing. In this case, number one was describing area. So we knew that area was going to be our primary equation, our equation of focus that we're focused on. So we see area is equal to x times y. There is too many variables on the right side. So this tells us that we need a secondary equation. We need something to give it support so we can get our equation down to one variable on the right side. So cost perimeter was the equation that we needed. So I isolated one variable, solved for one variable, plugged it in. And then once I'm at this point, you're going to begin to see that a lot of your problems are going to begin to look the same. Okay, it's all the same process. Clean up your equation, get it ready for power rule, find the derivative, solve for x, and then when you solve for x, you do need to go back, you do need to reread the problem and see, okay, what can I plug into to actually answer the question that the problem is asking for us to find? Is it asking for dimension? Is it asking for the volume? Is it asking for the area? Is it asking for the revenue? Okay, so, but everything that you need is going to be already in your problem. You shouldn't have to create anything else to find the answer. Once you solve for x, it should feel easy. I mean, you basically have the answer. You just have to kind of do some finishing touches by providing what the problem is asking for. So in this case, we want to make sure that we get to the so that all of our derivatives should feel like an easy problem. Go through power rule, find the derivative, set equal to 0, solve for x. And when we solve for x, I realize that it's asking for dimensions. So I need to find y as well. There is an equation for y, plugged in the 150 in for x, and then got my dimensions. Okay. So today, we're going to do some problems that are a little bit different scenario in the sense that after we set up our equation, we're going to realize that we won't need a secondary equation because everything is going to be already in terms of x. So we'll talk about those kind of different scenarios today. Okay, so we're going to skip number 2, but I'm going to use the space for number 3. So I can just have plenty of space to work through this problem. Okay. So let me read the problem. I'm going to draw out the scenario, and then we can talk about how to set up this problem, a problem like this. All right, so it says a piece of cardboard measures 10 by 15 inches. Four equal squares are removed from corners of all sides. Find the maximum volume. So let's have a visual with our cardboard rectangular piece of cardboard here. Okay. So let's say this is 15 inches. Let's say this is 10 inches. And what we want to do is we want to be able to cut out 4 equal corners. We don't know what they are, but we do know that they're all the same. So I'm going to call them all x's. And the goal is that the resulting shape is going to be something like this. And if you can imagine folding along these flaps, and then once we fold up the flaps, then you have a box, right? An open top box. So here's what we're trying to achieve here. We're trying to figure out how much can I cut out so that the resulting box that's created is going to give me the maximum volume that can hold the most stuff. Okay. So that's what we're trying to achieve. Right, so this tells us then that we're trying to maximize volume. We're trying to optimize volume. Okay, what's the volume formula of a box? What components do we need to find the volume of a box? Yeah. Yeah, so area of the base and height. So I'm going to say length and width to create the base and then the height, right? So length, width, and height, 3 dimensions. Okay, so let's see if we can create an expression that represents the length, that represents the width, and one that represents the height. So we start off with 15 inches. We cut out our x's. What's left over? What represents my length after I cut out the corners?
So L minus 2x.
Okay. Right, and then we'll use specifically 15 for our problem, but you're right, L minus 2x. Okay, what about the width? How much is left after we cut out from that side? 10 minus 2x. Okay, we fold the flap up. The flap is going to be the height, and what's the height of the box? X. All right, any questions there? Good. All right, so let's build our volume equation. Length, width, and height. I'm just going to put the height first just because the single term there. Which order you put it in, just my preference to put the single term in front. All right, so this is the equation that we have to eventually find the derivative for. Notice that we don't need a second equation, right? There's no y's, everything's in terms of x, we're good to go. We just have to clean this up to the point so that our derivative is just power rule, then find a critical point, set equals 0, solve for x, okay. But the way I'm going to clean this up is I'm going to just see if I can expand this or combine this into its own set of parentheses. That way I can just deal with 2 parentheses and I can FOIL from there, right? I could do product rule, but I think we've gotten to the point where we know we're just always going to, power rule is feasible, so we're just always going to work towards power rule. And there's no plus between my 2 expressions, so I don't have to distribute the x through both parentheses. So if I just distribute it through 1, I'm just trying to get it down to 2 parentheses so that my foiling process is a little bit cleaner. Okay, so now we're just going to FOIL, expand, combine like terms. All the parentheses we want to disappear so that we can do a nice clean power rule for each term. Everything is set up and ready. I think some students in the previous period were saying, well, can I factor a 2x out, an x out? Yes. Well, the reason why we don't want to factor at this point is because we're trying to go through power rule, right? We've gotten all cleaned up. If you try to factor a GCF out, then you have parentheses in the problem, and that just makes it more complicated for our power rule. So we are going to find factors, but not until we achieve our derivative, right? Let's get to our derivative first while it's in a nice clean format, and then we can worry about, factoring and all that. Okay, but we don't want to factor at this point, because if we do, then we've undone, the work that we wanted to do, so that power rule is manageable. If we introduce parentheses back into the problem, then we got to go through product rule, and we want to try to avoid product rule. Okay, so let's find v prime. set v prime equal to 0. Now we can look for a common factor if there's any, because we want to, solve for x. All right. Unfortunately, that quadratic expression is not factorable. So we got to go through quadratic formula here. There's my A, there's my B, there's my C. So this is going to result in two answers. One is 50 plus square root of whatever this mess is divided by 12. And then the other answer is going to be 50 minus square root of whatever this is divided by 12. Okay, I'm just going to skip to the end here. My two decimal values are 6.37. So this is what we get as potential x values to cut out from each corner. But one of them is going to be an issue. So look at this diagram here. Look at the potential x values. What do you notice?
If you cut 6.3715 out of the 10 inches, that'll just cut the end off.
Yeah, there's not enough material here, right? The 15 is not the issue, right? You can cut out 6 inches from both sides. You're still left with some material here. But if we only have 10 inches to work with, we can't cut out 6 inches and 6 inches here, right? Then that's more, we're cutting out more than what we're beginning with. So it's not feasible. The 6.3 is not going to work. Right? Logically, it just doesn't fit into our diagram. So the only option is 1.962. So out of all the possibilities that we can cut out, it's going to be 1.962 that will allow for the maximum volume, right? Will allow for the box to reach its maximum volume. Yes.
Why did you choose to use the quadratic formula?
I wasn't able to factor it. Were you able to factor it? I was just thinking, or maybe I was just looking at it saying, okay, I don't want to try to think of ways to factor it, so I'm just going to go down to quadratic formula. Yeah. Yeah, quadratic formula always works, but yeah, obviously, you want to try to avoid it if you feel like something is factorable. Now, does this answer our question? Having that 1.962?
No.
Okay, it's still asking for the maximum volume, right? So how can we use this, the amount that we cut out from the corners, to find the volume? Okay. Which one?
Length and height.
Yeah, good. So any of these, yeah, you can do length, width, and height. You can do any of these. All these are good. What you don't want to do is you don't want to plug into V prime, right? So V prime, that's something else, right? In fact, if you plug 1.962 into V prime, you should get zeros. That's not what we want. So any of these options are fine. But yeah, you could also find length, width, and height and multiply them together at the end. Okay, just want to make sure that we know where to look depending on what the problem is asking. So any of those options, we should get something like 132.038 cubic inches. Okay, any questions? Okay, let's look at number 5 and 7. 5 and 7 are also kind of very specific type problems that also are going to where we don't need a supporting equation. Everything is going to be in terms of x. So let's go to number 5. Does anybody still need to look at number 3? All right, so here's number 5. Okay, let me read the problem and talk about how we're going to set this up. So Highway 400 averages 54,000 cars per day for its first 5 years of charging 50 cents per car. Scientific research study concludes that for every 5-cent increase in the toll, the number of cars is going to be reduced by 500. Right? In order to maximize revenue, what toll should Highway 400 charge? So this is what's happening here. The idea is they're trying to figure out how to maximize. And one thing that they can do is just keep increasing the toll, right? If they keep increasing the toll, then assuming that there's the same number of cars coming through the toll, we should get a higher revenue. But the problem is that if you're raising the toll rate, then you're going to find other ways to get to their destination, right? It's going to come to a point where it's not worth it for a driver to, it's worth it for a driver to seek out alternate routes. So this, based off of this, they're trying to figure out what is that, how much can they raise the rate and still be able to maximize revenue. Okay. So let's talk about how to calculate revenue. So revenue is you take the total number of cars and then you multiply it by however much you're charging per car, right? But we're going to have some moving parts here because we're going to be involving toll increases, which is going to affect the cost and which is also going to affect the number of cars going through that toll road. So let's talk about how we can build our revenue equation here. Okay, so total number of cars. Let's start with the beginning here. How many cars in the initial scenario? 54,000. But with each toll increase, what's happening? Okay, so how can we involve that in an expression? Okay, minus 500x. Okay, let's talk about what this means. That means with one toll increase, I'm losing 500 cars. With two toll increases, I'm losing 1,000 cars. 3 toll increases, 1,500, okay, so on and so forth. Okay, so using this logic here, can we create an expression that represents the change in the toll charge? Okay, how much is the starting charge? Okay, 50 cents. Okay, how's the toll increase going to be involved here? Just 0.05x, but what do we do, plus or minus? Plus. Okay. Okay, let's test this out. Let's see if this makes sense. So one toll increase means that it'll be 5 cents plus 55 cents. So 55 cents, I'm losing 500 cars. 2 toll increases, that's going to go to 10 cents. So 60 cents, 1,000 cars, right? So you're always going to have this balancing thing where one is going down, the other is going up. Good. Notice that we have no y's involved. There's no need for a secondary equation. So just like with the volume equation that we had before, we just get this cleaned up, get it ready for power rule, find the derivative, set equal to 0, solve for x. All right, same process. Okay, so let's try that, see if we can work our way down to solving for x from here. But we're going to expand first. Okay. Find r prime, set r prime equal to 0, solve for x. Okay, solve for x. That's 49. Okay, so what does that number mean?
So the amount of times it can increase the total.
Yeah, before we start losing revenue, right? Or that we start maximizing revenue. So it's 49 total increases. Okay, so this is probably probably not a completely realistic scenario, right? Once it gets up to a certain amount of total increase, it's not just always going to be reducing by 500. It's probably going to start exponentially grow, and it'll probably be a lot, a lot sooner before revenue starts to drop. But for our purposes, we're just kind of getting used to, the setup, and we're just assuming that it's only going to be reducing by 500 with each total increase. Okay, so let's see. How can we answer the question now? It says, what toll should 400 charge? So 49 is not going to be our answer, right? How can we get to our answer?
So plug it into the second half of the Rx equation.
Good. So again, I just want to kind of emphasize that everything you need is already there. If you able to get to the x, everything you need is already in the problem. You just have to figure out where to pull it from. So this will give us the charge, the cost per car that will maximize revenue. If the problem is asking for how many cars is going to go through at the moment that you charge the optimal toll charge, you're going to plug into this expression, right? You want to find the total number of cars. If you want to find out the total revenue, then you plug into any of the revenue equations. So the total charge, $2.95, according to this research, according to this data, is going to be where we're going to still be able to optimize our revenue. After $2.95, then it's not, then our revenue, it won't be as much. Okay. All right, any questions with 5? Okay, so this is very specific scenario problems. Let's practice another problem like this. So let's go down to number 7. Yes.
Why is it only for
Oh, it says in order to maximize revenue, what toll? It's asking just for the toll charge. So the toll charge is the one that is involving the dollar amount. So 50 cents plus 5 cents times 49, we're gonna get $2.95. But if it's asking for the revenue, then you would plug into everything, right? It just depends on what it's asking for. Yes.
Are we gonna have like any of the minimum value questions to do, or because we've only done like maximum so far, but you brought up like the minimum.
We have, yeah, but the process is going to feel the same. There's no distinction between finding maximum and finding minimum. The process is still the same. Whenever you find slope 0, it's gonna help you reach that max or min. But you're right. Most of these are going to feel like in terms of maximum. The minimums that we've done is like cost effective. You know, what will allow for the minimal cost. So maybe we'll do a little bit more on Friday, but yeah, just want to let you guys know. Don't worry about max and mins. Everything will just work out the way it's supposed to. No, not a different process. Any other questions? Okay, let's look at number 7. I'm gonna help with your initial setup, but I want to see if you guys can use this model to help you finish the rest of the problem for number 7. Okay. All right, so we have a 150-room resort hotel. It is filled to capacity, and it is being rented at a rate of $125 per day per room. But they want to start exploring how can I maximize revenue. So they want to look to do some $5 increases with the room rate. But then they see that each $5 increase that they make, there are 3 fewer rooms rented, right? You have customers who are going to explore other options if it continues to rise. So what room rate will result in the maximum daily revenue? How many rooms will be rented at that rate? So we're going to set up our revenue equation in a similar fashion. Right, your revenue is calculated by the number of rooms that's being rented multiplied by how much you're charging per room. So see if you're able to use number 5 and the setup that we talked about. Can you create those expressions that represent the change in the rooms rented based off the rate increase and the change in the room rate based off the change based off the rate increase? Okay, what expressions you guys find for number of rooms rented? Okay, 150 minus 3x. Okay. How about the room rate? Plus 5x, right? We expect that. We want one to be subtracting, one to be decreasing, we want one to be increasing, right? Expand. Get ready for power rule, derivative. But there's going to be something a little strange about our answer. We'll talk through that after you guys find your x. Okay, what did you guys get for x? Yeah, what's strange about 12.5? It's decimal, right? We only define a rate increase in terms of a whole rate increase, right? $5. We didn't define it for $2.50. So what that tells us is that we're not able to reach that optimal rate increase because it's just not defined within our parameters. But we do know that we're dealing with a parabola. We do know that we found the maximum point where the slope is 0. We're not able to reach that perfect place of optimal productivity, but maybe we can just choose values around it. We know that if 12.5 is the highest point, then 12 and 13 should be the next best options, right? So why don't we test that? Why don't we see which one gives us a better revenue option, the 12th or the 13th rate increase? So why don't we plug 12 into one of our revenue equations and see which one gives a better, brings in more money. Okay, what you guys find?
They're the same.
They're the same. Okay, so it's pretty symmetrical. So it doesn't matter if it's a 12th or the 13th rate increase, we're going to bring in the same amount of revenue. Okay. All right. Now, does that answer the question though? What room rate will be results in a maximum daily revenue, or how many rooms will be rented? We still got to plug in either 12 or 13 into one of these expressions, right? So let's say we choose 12. Okay, you can do 13 if you want, but let's say we choose 12. So we can plug 12 in here to get the rooms rented. We can plug 12 in here to get the room rate. We can, and then we already know the total revenue, right? So okay. So I did it for the 12th room rate increase, but if you plug in for the 13th rate increase, the rate and room will be different, but it'll still be correct. Oops. Okay, any questions? Yes.
Could you just explain that?
what they represent. Okay, so we know that we can't do 12 and a half, right? But we know that our next best option is going to be either the 12th rate increase or the 13th rate increase. So right now we didn't know which one has the better revenue. So I plugged 12 into one of the R of X's, either either the factor form or the standard form, and I got 21,090. So that's how much money I'm able to bring in at the 12th rate increase. That's the total, right? At the 13th rate increase, I'm also bringing in 21,090. So it doesn't really matter whether I do the 12th or the 13th rate increase, I'm going to be bringing in the same amount. So in order to find the room rates and the number of rooms, we can either choose to have X equal 12 or X equals 13. They're both correct. I just decided to choose 12, which is the first number I saw and it's a smaller number. So if I want to find the rates at the 12th rate increase or the room rented at the 12th rate increase, I can plug 12 in for X and I'll get 150 minus 3 times 12, and that gives me 114 rooms. And then if I want to find the rate, I plug 12 into the 5X plus 125, and that gives me how much I'm going to be charging per room. 185. Okay. Good. Any other questions? Okay. All right. Let's try one more problem. Let's try number 8. Number 8 is going to be more similar to what we've already done yesterday and at the end of class yesterday. This is where we're going to be pairing area with perimeter. So it says a farmer has 400 feet of fencing to make 3 rectangular pens. So here is my drawing of the 3 rectangular pens. What dimensions of X and Y will maximize the total area? So I called my horizontal X, I called my vertical Y. I also have fencing in between to separate and create 3 individual regions. So we want to maximize area. We know area is going to be our starting equation. So what's the area based off of this diagram here? XY. Okay. So we see that we need some support, right? This too many variables on the right side. We got to get it down to just in terms of X or just in terms of Y. So the help is going to come from the perimeter. So look at how much fencing is here. How would you create your perimeter equation?
2x plus 3, 4y.
Good. So we have 2 horizontal and 4 verticals, right? So 2x plus 4y. And what do you know about perimeter? How much fencing?
400.
400. So there's our path to towards our answer, right? Let's get this in terms of I'm gonna look to replace y. So I'm going to solve for y, make that substitution, power rule, or expand, get away from power rule, derivative, set equals 0, solve for x. Okay, so see if you guys can finish this problem from here. Okay, check your answer. Any questions? Okay, you guys okay? All right, so I think you've seen all the scenarios that we need to go over with optimization. So Friday we'll do our test review. I'll make sure the links are ready for Friday, so you can have all that printed out, ready for Friday. All right, if there are no more questions, then if you're on Teams, you're free to go. Have a great day. See you guys Friday.